Hey everyone. So this short lecture is on Bowen's reaction series. Norman Bowen did some seminal work in the 1920s, and he was an experimentalist. And what that means is he literally collected igneous rock in the field and melted it in the laboratory to see which minerals would crystallize at what temperature. And the diagram that you're looking at right now is known as Bowen's reaction series. And the take-home message here, the all-important take-home message that Bowen figured out is the crystallization order of the big 8 silicate minerals. These are the most common silicate minerals that you've already learned about. And thanks to the experimental work that Bowen did, we now know their order of crystallization with respect to temperature. You can see on this diagram that up at the highest temperature, starting roughly at 1200 degrees, as a magma cools, as Bowen's experimental magma in the laboratory cooled, Bowen noticed that the very first mineral to crystallize out of that cooling liquid was olivine. Olivine is a ferromagnesian silicate mineral, as you know, and starting with what Bowen called the discontinuous series, Bowen noticed that olivine was, of course, the first mineral to crystallize, and then after olivine stopped crystallizing, another mineral, pyroxene, would start crystallizing at a lower temperature. And pyroxene would crystallize for a while, and then when the temperature got low enough, pyroxene would stop crystallizing, and amphibole would start crystallizing, so on and so forth, all the way down to biotite. So this left-hand branch of the reaction series is known as the discontinuous branch, or the discontinuous series. It's called that because one mineral gives rise to another mineral in kind of a stepwise fashion. Literally, at a certain point, as we went over, one mineral will stop crystallizing and a completely new mineral will start crystallizing. That's called the discontinuous series. Bowen also noticed, however, that at about the same time that olivine and pyroxene and amphibole and biotite were all crystallizing out of the melt at different temperatures, another important mineral group was also crystallizing, the plagioclase feldspar mineral group. But in contrast to the left-hand branch, in contrast to the discontinuous branch, Bowen noticed that over this range of temperatures, the actual mineral didn't change. You can see on this right-hand branch that it's plagioclase all the way down from high temperature down to low temperature. So it's not the mineral itself that changes. Instead, what changes in a gradual, continuous way is the composition of the mineral. And at high temperature, Bowen noticed that the first plagioclase crystals to form in the melt were calcium-rich. And then at lower and lower temperatures, as plagioclase was crystallizing more and more, it was becoming more and more sodium-rich, so that by the time you get down here to about the same crystallization temperature as biotite, the plagioclase that's now crystallizing is sodium-rich rather than calcium-rich. And right here in the middle, what's happening in here? Well, at intermediate temperatures, the plagioclase that's crystallizing is both calcium and sodium rich. It contains both. So in other words, in the continuous branch, there's a continuous change in composition to the plagioclase crystals that are crystallizing out throughout this entire range of temperatures. And then Bowen noticed that the very last 3 minerals to crystallize out at an even lower temperature included K-spar, potassium feldspar, muscovite. You might remember that muscovite is a non-ferromagnesian mica mineral. It's kind of like biotite, except for the fact that it's a non-ferromag silicate, meaning muscovite doesn't contain any iron or any magnesium. And then finally, Bowen noticed that the very last mineral to crystallize out of the melt at the lowest temperature of all is the mineral quartz. And notice on these big bold arrows, what's being indicated here is that up here at high temperature, the minerals tend to contain iron, magnesium, and calcium. And then as the temperature drops at lower and lower temperature, the minerals are more enriched in potassium, sodium, and aluminum, and also silica itself. Remember that in the case of igneous rocks, when we speak about the silica content, that's really just a generic way of referring to the silicon plus the oxygen in the rock. And so the mineral quartz, for example, with a composition of SiO2, can be described as pure silica. Okay, let's move on here. So again, the take-home message is that we now, thanks to Bowen, we know the order of crystallization of the common silicate minerals. And an easy way to remember this, by the way, is to remember this phrase, OPAB, CAP, NAP, KMQ. Let me say that again. OPAB, CAP, NAP, KMQ. The O stands for olivine. The P stands for pyroxene. The A for amphibole and the B for biotite. CAP refers to calcium-rich plage, whereas the NAP refers to sodium-rich plage. And you can probably guess by now that the KMQ here refer to K-spar, muscovite, and quartz. So that's a really good way of remembering the order of crystallization of the common silicate minerals. OPAB, CAP, NAP, KMQ. All right, let's focus a little bit more on the discontinuous series, the discontinuous branch. So what I told you before is certainly true. Olivine will crystallize out over a certain range of temperatures, and then when the temperature gets too low, olivine will stop crystallizing and pyroxene will start. And then when the temperature gets too low again, pyroxene will stop crystallizing, amphibole will start crystallizing, and so on and so forth, all the way down to biotite. Interestingly, what Bowen noticed, however, is it's a little more complicated than that. What actually happens is when olivine gets down to a certain temperature, not only does olivine stop crystallizing, but even the olivine that's already crystallized will react back with the remaining magma and actually convert itself into pyroxene, and so on and so forth, all the way down to biotite. So, for example, when pyroxene gets down below a certain temperature, the pyroxene that's already formed will react back with the magma to begin to convert itself into amphibole. And likewise, the amphibole at a low enough temperature will react with the magma to begin to convert itself into biotite. How do we know this? Well, Bowen himself noticed that when, for example, he fished olivine crystals out of the magma, he noticed that in many cases there was a central core of olivine. That's the reddish crystals here. And then this central core of olivine was actually surrounded by a rind, if you will, of pyroxene. Those are the bluish crystals in this false color diagram. So again, the discontinuous branch tells us that certain common ferromag silicate minerals, olivine, pyroxene, amphibole, and biotite, will crystallize in a stepwise way as the temperature is reduced, and also that higher temperature minerals will begin to convert themselves into lower temperature minerals as this process proceeds. Well, let's move on to the continuous branch. Here it's a little bit different, and we know this, and Bowen realized it as well, when we focus on the actual composition of the central core of a plagioclase crystal here versus the outside of the plagioclase crystal. Keep in mind, this entire crystal that you're seeing is plagioclase from the inside to the outside. But when Bowen analyzed the composition of the interior of the plagioclase crystal, he found that it was more calcium-rich. And then as crystallization proceeds, and you can actually see the different crystallization lines, kind of like the rings of a tree, Bowen noticed that the outer edges of the crystal that crystallized later at lower temperature tended to be more enriched in sodium as opposed to calcium. But keep in mind here, the change from calcium-rich plagioclase to sodium-rich plagioclase isn't happening in a discontinuous or stepwise way. It's happening in a gradual, continuous way. In other words, the crystals are changing composition continuously as they solidify out of the remaining magma. So that's a quick summary of sort of the different characteristics of crystallization in the discontinuous versus the continuous branch of Bowen's reaction series. Okay, well, to return to this all-important diagram, and I'm going to keep emphasizing this, what does it tell us? Well, the most important thing is it just tells us the crystallization order with respect to temperature of the common silicate minerals. Some of these are ferromag silicates, including olivine, pyroxene, amphibole, and biotite, and all the others are non-ferromag silicates, including plagioclase, K-spar, muscovite, and quartz. How do you remember the order of crystallization overall? Just focus on this, this mnemonic, OPAB, CAP-NAP, KMQ. Remember, the O is for olivine, the P is for pyroxene, the A is for amphibole, the B is for biotite. CAP is for calcium-rich plag, NAP is for sodium-rich plag, and then finally KMQ is for K-spar, muscovite, and quartz. One other really important finding of Bowen's reaction series is it allows us to make accurate estimates of what minerals are likely to be found in what rocks. So for example, if we have an igneous rock of mafic composition, all we do to estimate the mineralogy of all mafic rocks is we just see what minerals correspond to the mafic band, that sort of upper row of Bowen's reaction series. And you can see here that according to Bowen's reaction series, mafic rocks like gabbro and basalt tend to be enriched in olivine and pyroxene and calcium-rich plagioclase. Likewise, igneous rocks of intermediate composition, like diorite and andesite, tend to be enriched in amphibole and also plagioclase that is both sodium and calcium rich. And then because the boundaries here between mafic and intermediate and felsic aren't exact, that's why the lines here are dashed, we actually would expect a little bit of pyroxene sometimes in rocks of intermediate composition. And then finally, when we get down to felsic rocks that are forming at relatively low temperature, these rocks, like granite and rhyolite, for example, tend to be enriched in low temperature minerals like biotite, K-spar, muscovite, quartz. Typically, felsic rocks also contain a lot of plagioclase, but the plagioclase feldspar tends to be enriched in sodium as opposed to calcium. So that's the other big take-home message here with Bowen's diagram, is you want to make sure for rocks of mafic, intermediate, and felsic composition, you can say something about the mineralogy of rocks of these compositions. And to get that information, it's all right there for you on Bowen's reaction series. Good luck.